evening. I'm sure you people are ready for your dinner. And I thank the organizers for asking me to give a talk. I just arrived from USA and I have to stay home, so I can't be with you in person. So next slide, please. Next page. Can you, Nitesh, can you go to next page?
Yes, sir.
Yeah. Please, next page. Okay, a brief outline. First, I want to tell you a little bit. No, previous page. Outline, please. Just a page before.
Yes.
One before. This one. So I want to first tell you a little bit. No, second one. It goes away quickly. This one. So what is magnetic exchange, magnetic coupling? What is the physics of it? And how it controls the magnetic state. That's point number one. And I want to talk to you about concept of super exchange and how it is related to hybridization between atomic wave function or orbital. And then I'll address the issue, what I call D0ness, and how I can use it, or one can use tuning this magnetic exchange. And finally, I don't have time, but there is a lot of exciting thing going on now in the field of this spin system, particularly when the spins are quantum. There is what is called a quantum spin liquid state, which has a lot of exciting physics and topology, and I won't have time to talk about it tonight. Now, next page, please. Nitesh, next page.
Yes, sir.
Okay. Now, normally, there are many energy scales in a solid. You go to deep cores, forget about nuclear and quark energy scales, GeVs, but there are electron volt energy scales, atomic orbitals. Then there is a tenth of an EV energy scale, like band gaps and so on. Then there is a magnetism, which is a milli-electron volt. So, as you know, although the microscopic origin of magnetism is in all this high energy, atomic energy level, energy scale, a lot of physics can be understood in an effective theory called effective Hamiltonian, and that's what we use many times in studying magnetism. I'm not going to talk about metallic magnetism like iron, cobalt, and nickel. And I'll talk about a crystalline solid. So they are ordered solid. And at the atomic sides, with the crystal sides, there are magnetic moments, which I can represent by something I call a vector. The spin. Associated with the spin will be a magnetic moment. The real physics is the coupling between magnetic moments, but I'll call it as a coupling between the spins. Excuse me. So now the effective theory, which describes the magnetic property of a solid insulator, a magnetic insulator, I call it H spin, which is a coupling constant between between spin I and spin J. And they can be anywhere in the lattice. They can be nearest neighbors, next nearest neighbors, long distances. That is determined by the Jij. So Jij is called exchange coupling or magnetic coupling. And SI and spins can be classical spins and quantum spins. As you know, in any problem, classical physics is easy to solve and understand, and quantum problems are hard. But even this simple-looking Hamiltonian is extremely complicated, particularly when we are talking about large system, infinite system. It's a many-body problem, and as you know, the exact solutions of many-body problems are very difficult. So there are four fundamental questions I want to address in this lecture. One question, and people have worried about it for a long time: what is the nature of the ground state? How the spins order? Given a lattice site I and J structure, given Jij, can I find the ground state? This is a challengingly difficult problem, but I will address a few simple questions on that. The second question I want to address today is origin of these local moments. Where do these magnetic moments come from? And they come from atoms, of course, but why don't they lose their atomic magnetic moment in a solid? So there is a lot of thinking to do, one has to do to understand the origin of these localized moments. The third thing is origin of the insulating state. I'll just briefly touch it because that's a very important problem in condensed matter physics. What is the origin of an insulating state in these magnetic insulators? Naively, they should be metals, but they are insulators. And I'll briefly show one or two slides. And then finally, I'll talk about the origin of the coupling, JIJ, what is the microscopic physics. And that's where I will talk about the de Gironès and how I can tune them or couple. Okay, next slide, please. Next slide. Nitesh, next slide.
Yes, sir. There is a little bit lag.
Okay, that's all right. Okay, that's all right. We're all delayed. Okay, here is a very simple example. I want to show you how the problem can be very complex. Let's look at a simple chain of magnetic moments, and there is a coupling. The Hamiltonian is that there is a coupling between nearest neighbors, Si plus 1, and there is also a coupling between the next nearest neighbor, Si and Si plus 2. Now imagine a situation, and J is the overall strength of the coupling parameter, and beta measures the relative strength of the second neighbor to first neighbor. Let's put beta equal to 0. So suppose if J is positive, then the spins would like to be antiparallel because the energy will be minimized when there is antiparallel. That's called antiferromagnetic coupling. But if J is negative, the spins would like to be parallel, ferromagnetism. All my lecture today will be associated with J, which is positive. And that's where a lot of exciting physics comes in. And the system is an antiferromagnet. Okay. Now, the other thing you have to think about, these vectors can be three-dimensional. That's called Heisenberg model, Heisenberg spin. They can be three-dimensional. Or they can lie in a plane called two-dimensional XY, or they can be along a line, something called Ising. So whether it is a Heisenberg or XY or Ising, depends on local physics. Let's look at the very simple problem. Let's say J is positive, and beta is, you start from very small beta, and so there will be, as I said, it will be an antiferromagnet. Now you start increase beta. Now you see what happens. The nearest neighbors like to be antiparallel. That's very good. But the next nearest neighbor, you see they become parallel in this configuration. So, the beta term doesn't like it. So that's called frustration. So an important part of magnetism now to understand the role of frustration. In old days, we used to call it competition. So what you find that if you turn on the beta, increase the strength, suddenly the frustration starts to become very important, and the ground state is no longer an up-down antiferromagnetic state, but becomes a spin spiral with some chirality. Spins start spiraling around in one direction. And that spiraling and the order also depends heavily, if I'm talking about a Heisenberg spin, then it's a nice spiral because three-dimensional spins are very nice to move around freely. But if you make it an Ising, which can only become up or down, then the ordering is very, very strange. Up, up, down, down, up, up, down, down. So you see here, just the competition and the local constraint, which keeps the spins in three-dimension, two-dimension, or one-dimension, will dramatically change the nature of the ground state. And this problem, of course, now many real systems are very different, competing frustrations, and a lot of interesting research is going on nowadays in this area of frustrated magnets. Now let's go to the second, next slide, please. Because,
Yes, sir.
okay, here I want to show you, I always show this one, particularly to make the young students like you excited. the first author in this paper is a young undergraduate, a girl who came to work with me, and the second author in this paper, he was very well-known physicist in magnetism, very close friend of mine. We worked together, and he passed away 3-4 years back. So this girl came and said she wanted to have a project. And we were working on many things. We gave her a very simple project, and where you take what I've done, I've added to the first term, J1, nearest neighbor, Sn.Sm, a quadratic term. There's nothing much. There's a quadratic term, and there's other ones are simply the similar physics of frustration. So we asked her, can you solve this problem? And we told her a method, right? We can formulate the problem. And she took it in 3 months. She came out with so many important results. It was an undergraduate, which is second year physics, and she published this paper in Physical Review Letters. And this paper helped her to get admission into Princeton. Not this paper, she's a bright girl. And then now she's a very well-known physicist. I don't know what she's doing, but I tell you that there are interesting problems. Young students can do it. Now, what I want to show you, this is a little complicated Hamiltonian. It's a two-dimensional system. Lattice is two-dimensional, and still the spins are vectors, isotropic, but the phase diagram, as you change the parameters, are completely fantastic. So can I go to the next one, please? Yes. Next slide. So you see here, so we take two models. I told you XY, when spins are only in a plane, which is like a two-dimensional spins, and the other one is Heisenberg, which is three-dimensional spins. The phase diagram is quite different, but you can see the exotic spiral phases which come out exactly as the new ground state. Of course, some of them, when we wrote that paper, it was a theoretical calculation. Over time, with expert chemistry, people have started making some systems which can prove some of these ideas. So the point I want to make here, the spin, even a simple spin Hamiltonian magnetism, it's a many-body problem, and solving for the ground state is challenging and not always possible. And sometimes you can solve it. And the other important point to understand here, or interesting thing, if there are classical problems, you can solve it slightly easily. You can solve it. But if the quantum problem, quantum problems are harder to solve because of the commutation rules and fluctuations. So the role of quantum effects is still a point of current interest. But I will stop here and just summarizing that the nature of the coupling between the spins determines the ground state, and frustration can be very interesting, or computation, and that can create many exotic ground states. And if I don't know whether one of your speakers, I think, who is working on these systems, might have talked about this exotic ground states of this quantum spin system. Now let's go to the next problem. Next problem. Next slide. So let me discuss a little bit about the fundamental question which I put in the beginning. 2. What is the origin of the local moments? So let's take an example, iron oxide or manganese oxide. Where is the magnetism is coming from? And so basically the real magnetism comes from the atomic physics. Manganese atom is a magnetic, can be magnetic, and oxygen is not. So basic chemistry. So the chemistry is playing a very important role. And my last 15 years, I've been working a lot in collaboration with chemists because they understand the materials very well. Now, a very simple example is manganese oxide. You take manganese, you take oxygen, you put it into a solid. Oxygen likes to fill up its two shells, the full p shells, likes 2 electrons. So manganese gives away 2 electrons to oxygen. Oxygen is filled shell, neutral, magnetically neutral. Manganese is 2 plus, and 2 plus is 5 d electrons. And these d electrons become magnetic. and you must have heard about Hund's rule. Hund's rule plays a profound, important role in the physics of local magnetism. So what happens, if I have 5d electrons in a d shell, all of them like to be parallel because of the Hund's rule, and that leads to the moment of 5-half. And of course, if the d orbitals are full, no orbital angular momentum, so the magnetic moment becomes 5. A spin is 5-half. The other magnets is easy, but the other ones are a little tricky. For example, copper oxide or cuprates were very famous for high temperature conductors. There, the copper is 2+ ion, 9 electrons. So, okay, you can fill it up. The spin is half, very easy. But the orbital angular momentum, if it's an atom, it will be ml equal to 2, so it will be 2. But in the solid, it's not there. So solid, as you know, something called a quenching of the orbital angular momentum. What it means that if I put an atom in a solid, the electrostatic fields produced on the atom by the local crystal field tries to pull atoms in different electrons in different directions. Net effect is to quench the orbital angular momentum around the nucleus. So that's an important thing to understand in solids. The atom you can put in, but you have to allow for the fact these atoms are not free atoms, or ions are not free ions, but they're in a crystalline field. And that usually quenches the orbital angular momentum, but keeps the spin. So that one has to worry about when you do the magnetism of complex systems. So atomic physics with crystalline effects determine the magnetic moment of in the solid, the real solid. Okay, chromium, I'll show you, let me tell you a little bit, later I'll bring it back. The chromium is S equal to 3/2 because there are 3 electrons. I'll come back to this one of my last slides. Okay, next slide please. Just before I go, so copper is half, spin half. Chromium is spin 3/2. Manganese is spin 5/2. So manganese spin S is large. It turns out in quantum spin systems or spin systems, as you make S larger and larger, you can think of they behave more like classically. And this, the spin half, which is copper, is the most quantum, shows the most quantum effect, most quantum fluctuations, whereas it starts to becoming semi-classical. And that's, so classical, semi-classical theories are good for manganese, but not for copper. Okay, so now let me go to this most other important question of great interest in condensed matter physics. It's a manganese oxide. As I told you, 5d electrons and oxygen is full. So if you think of it, manganese in an atom, it is 5d electrons. But when you put the manganese in a solid, it becomes a d band. And d band has 10 electrons, right? There are 5 orbital states, and for each orbital 2. So there are 5 states. So the d band will be 5, can take 5 electrons. But I have only 5 electrons, and d band can 10 electrons. So the band should be half full. So a typical naive way of thinking, the manganese oxide should be a metal, and it should be just like a picture I've shown, something called a density of states, shows that the oxygen band is completely full because, and the manganese band, which is a narrow, because d electrons are more localized than the oxygen, so they become half filled. But that's not the real system. So that's where the whole many-body physics, correlation physics comes into picture. Because the d electrons, the d orbitals are very localized, when the electrons in a band state, they can move around freely, and there's a large probability the 2 electrons will be at the same site. So there'll be a strong Coulomb repulsion, and that forces the electrons to keep away from each other, and that leads to what is called Mott-Hubbard physics. That band in a many-body theory splits up into 2 bands, and the lower band can have 5 electrons, upper band will have 5 electrons, and that's what leads to an insulator and magnetism. So that's known in the literature called Mott-Hubbard physics, and the strong Coulomb repulsion is called U effect. So you might have heard lectures on this. So to understand the magnetism of insulators containing unfilled d electrons, d shells or f shells, we must have many-body correlation effects essential. Otherwise, they'll be better. Okay, next slide. So now that you know that what causes an insulator, manganese oxide. Now I know you also know what leads to magnetic moments, atomic physics with crystalline effects, bunching of orbital angular momentum. Now, next question is, how do they couple? How do they couple? Because, as I told you in the beginning, the coupling determines the physics of the ground state of magnets. One of the simplest understanding of coupling came from a very well-known physicist called Anderson. And the idea was, people understood the standard. If you remember, in Hartree-Fock type many body theory, there is a Coulomb interaction, exchange interaction. Those are well understood. But Anderson came into a beautiful, important picture called kinetic. In solid, something called a kinetic exchange. Here is a picture, very simple picture. Imagine two d electrons, one at one side, one on the other side. Now, suppose they are parallel. If they're parallel, this electron from one atom cannot hop to the other side because of Pauli principle. I'm talking about a single orbital. So Pauli principle will forbid the hopping. On the contrary, if they are antiparallel, then they can hop. As you have all learned in quantum mechanics, of course, they will hop to an intermediate state. In the intermediate state, there will be two electrons at the same side. That costs you Coulomb repulsion energy. But in a second order quantum mechanical perturbation theory, the energy will be lowered by minus T square over U. That's the second order perturbation theory. So the fundamental, there will be a kinetic movement, a kinetic energy contributing to the exchange if they're antiparallel. If they're nothing, Pauli principle will forbid their parallel. So that leads to the fundamental antiferromagnetism in insulators. And Anderson got Nobel Prize for this ideas. Now, what about for ferromagnetism in insulators? That's a little bit tricky. So there, you have to wait with me. So there are two F, just like D. So direct hopping between them will give rise to antiferromagnet. But on the other hand, F's can't hop. There are some low-lying excited states. So now they are empty D0. So if it is available, one F electron from up will run hop to the other side, and at the same side they will have Hund's rule, and they will like each other. So this exchange to an empty D level was first proposed by Kasuya, and that leads to ferromagnetism. And it is well known in rare earth oxides. So there are two mechanisms. One is antiferromagnetism, due to direct hopping to the same orbital, and ferromagnetism hopping to the empty orbital. And there are many. So this direct hopping may not be there, but next slide will show you a little bit more exotic form of that. Can I show the next one? Yeah, here. So here in manganese oxide, the real system, the manganese are pretty far, so they can't talk to each other. So there's an oxygen. So, but the same physics what Anderson pointed out works here. Imagine two manganese atoms, one up and one down, and in between there's an oxygen atom. So, and an oxygen atom has two spins, field shape. It's possible what happens when one is up, one is down, one of the oxygen electrons can hop to the left and the up to the right. Pauli principle will not be violated. You will have exchange, kinetic, and there will be logic. So this is called super exchange. Super exchange because it is going through a third intermediate atom. And the super exchange is really the origin of magnetism in this component. And this is where hybridization takes place. Because D has to hybridize with P, and P will have to D. So that's the concept of hybridization between manganese D and oxygen P. But when talking about controlling hybridization, if I can tune this, I can tune the magnetic exchange. So one more thing to point out, there's a tremendous development in the area of magnetism using density functional theory. And density functional theory has become a very successful theory. I'm sure some of your faculty members worked on this, and they have been able to explain from a microscopic origin the small energy scales of magnetism. So let's go to the next one to talk about a little more interesting physics. Next slide. Now here I want to show you a very interesting point. It looks like a complicated system, but if you are a real magnetic person, you will throw away everything, only look at the magnetism. So the copper is the magnetic atoms that forms this blue chains. So how they couple through oxygen, germanium is complex physics, but the real geometry of the magnetism is through the chains of this coppers, and this has become a very important system because coppers are in half. These are one-dimensional, and they have become extremely quantum fluctuations. And so the point to emphasize here, the local geometry of copper, oxygen, germanium controls the coupling, but the global coupling between the copper atoms controls the ordering. So if you want to understand the physics of this system, you must at least be aware of the local coupling, local chemistry, and also the global, the many-body physics. This is where chemistry and physics comes to picture, and the coupling between experiment and theorist also come into picture. So I won't discuss about this, but we can compute exchange energies and work out the physical properties of this complex system. Let's go to the next one. I'll show you some results here. Next one, please. Okay. Before I go to the D0s, how much time I have? Nitesh, around 10 minutes?
Yes, sir.
Okay, 2 minutes. So let me tell you about this D0s. Remember I told you about hybridization between p electrons and the p electrons. But also you can, now there is something called a D0, and that was known to drive ferroelectricity. Barium titanate is a very important compound, and that is a ferroelectric. If you cool it down, there is a distortion in the lattice, and they become ferroelectric. Ferroelectric, as you know, can only arise if you break inverse symmetry. There will be some local electric dipole moment. Now, the physics of that was understood that the titanium atom, which is the d electron in the system, has an empty d level, which is low line. So an empty d level, which is low line, and the oxygen loves to hybridize. So what oxygen does, moves out from its center symmetric position and goes and hybridizes with the d and lowers its energy. So it's like energy lowering is the fundamental concept we always use, and so it distortion costs you energy, but hybridization lowers the energy and leads to a dipole moment, so that net energy is gained to this emptiness, this displacement. And so the cause of that is called the D0ness. If you take an atom where titanium replaced by something where there is no D, which is like a manganese, there is no ferroelectric. So this concept was known. So when we were working on this, we saw some experiment results, and I came up with the idea that maybe this D0ness might be playing a role in magnetism also. So D0ness can play a role in electrical moment, local electrical moment, local lattice displacement, and long-range order, electrical order, ferroelectricity. It can play a role in magnetism. So that is the story I want to tell you in the next 5-10 minutes. Can you show the next one, please? Okay, here is just a story. The PD hybridization and D0ness are essential for understanding ferroelectricity there. So now let's go to next one. Can you let me turn on the light? It's now getting dark. Okay, there's a light here. Can you see me a little better?
Yes.
Okay, so the idea of this manganese, which has no empty D, does not distort, doesn't show, but titanium does. So let's see how it impacts the magnetism. Next slide, please. Nitesh, next.
Yes, sir.
Okay, here is an actual experiment, And I got involved with this with a very close experimental friend of mine. And here is a compound. As I remember, I told you chromium, and X and oxygen. So X is some two different type of atoms. Oxygen is there, and chromium is there. What happens is that what we found experimentally, that if X happens to be a tellurium atom, it's an antifer. Okay, basically, let me explain to you the geometry. This basically consists of these blue atoms are magnetic chromium atoms. They form sort of a layers, and then another layer, bilayer, they couple. So what they found, and the golden atoms are these X atoms. They can change. So if X happens to be a tellurium atom, these layers are antiferromagnetic. The moment you make them tungsten, they become ferromagnetic. So that was very puzzling, and he came to me and we started thinking about it, and so we started to get some physical ideas, and we came up with the following explanation. What is the physics? And I related that to D0s. When we did these calculations, can you show the next graph, please? Next graph. Yeah, here is this switching from antiferro to ferro, magnetic coupling in an insulator. So you look at the tellurium, which is the B, and you see the bilayers are antiferro, but they're coupled, of course, with antiferro. Don't worry about that one. And the moment I go to tungsten, the bilayers become ferro. So the intra-bilayer exchange between two chromium is through oxygen, not through tellurium tungsten. So tellurium tungsten don't really matter. So what is the origin? So what our idea was that between tungsten and tellurium, there must be some fundamental difference. And it turns out there is an empty d orbital of one of the atoms, and that plays an indirect role in driving this magnetism. Can I show the next slide? Next slide, please. Yeah. So what you can see, and here is I want to tell you that 6 years ago when I started my PhD, density functional theory was coming into vogue, but nobody knew that it will, in the end, in 6 years, will provide you a fundamental understanding of magnetism. You just do the calculation. What you find by going from tellurium to tungsten, you see these bilayers, red, blue are up, down, and blue are all ferro. So switching just the tellurium to tungsten, you dramatically change the ordering or the nature of the exchange coupling. So, and you can find real ground states, one case seen in the experiment. So the theory and experiment do agree, and the physics is in the next space. Can I go to the next space? Can I show the next space, please? Yeah, here you see the fundamental difference in the tungsten case. There is a very sharp empty d orbital, just like the titanium had for the barium titanate. This empty d provides a venue for the oxygen to throw away the electron, hybridize, and the empty holes created in the oxygen drives this ferromagnetic. And we understand that was published in Physical Letters, and I think people have used that later in many other systems. The next slide, please. Next slide.
Yes, sir.
Okay. It's a simple physical picture. Antiferromagnetic coupling between superexchange, chromium-oxygen superexchange, and ferromagnetism between oxygen and tungsten, because what happens, tungsten has an empty d orbital, oxygen loves to hybridize with that, gives away. Hybridization means you're virtually taking an electron to that orbital and creating an empty hole in the oxygen level that drives the ferromagnetic exchange. And this is, we predicted using this. What about molybdenum, which has to be also a d orbital, empty, would be ferromagnetic. It was then synthesized and proved our theoretical predictions. Next slide, please. Next slide. I think I have 2 or 3 more slides, perhaps. Okay. I want to tell you about a very interesting, same physics has gone into this copper system also, but now copper is a quantum spin. So what happens, again, changing tellurium to tungsten, you tune the magnetism from ferro to antiferro, and some experimentalists became very bold. They made an alloy next slide, they made a 50% alloy. Can you show it? So and they found this is still, I think a Nature Communication paper came out in 18, so there's still a lot of work theory has been done. By making 50-50, think of a random system where there's an oxygen, tellurium, there will be antiferro, where there will be this, so there will be a spin disorder, and that leads to the ordered states becoming unstable towards a disordered spin liquid. So their prediction is spin liquid-like state in a spin half square lattice antiferromagnet induced by D0 or D10 mixing, and this is the idea which we proposed for the chromium. So now this is being used for the real quantum system. So I'm hoping, and I'm thinking a little bit about this problem, but I don't have any ideas. But I think we have seen similar thing in the chromium system, but they're not quite quantum spin liquid. Can I go to the next slide, please? Is there anything? That's the last one.
Yes, sir.
Yeah, well, anyway, so let me summarize. The idea of D10, D0ness, which was very important in explaining the ferroelectricity in titanates, I think they're very important in tuning magnetic coupling, and they've been used heavily in tuning magnetic properties. But I think their impact is going to be on these alloy systems where you can tune some ferro and antiferro and create frustrated systems which may show quantum spin liquid behavior. And that's the hope, and we'll see. Thank you very much. I'm sorry I could not, it was a little bit of a hurry up, and this is my experimental verification, which I don't want to show it to you, that indeed there's some fundamental property of a spin liquid is low temperature heat capacity, and that is what is seen experimentally. Okay. Thank you very much. And Nitesh, thanks for showing the operands, and I'm sorry I couldn't do it. That has happened in the past all the time.
Thank you, sir.
Okay, thank you very much.
Thank you. Now, students are interested.
Anybody has a question?
Yeah. They are interested to ask the questions. Sir, I have just small doubts.
Hi. I can't hear you.
Good evening. Sir, how the inversion symmetry driven by the D0ness against the
Nitesh, can you turn? You are muted. Oh, sorry. Just a minute. Yeah. Can you ask the question? Yeah.
How the inversion symmetry driven by the D0ness against this?
So what happens in the ferroelectrics, it is easy to understand. Normally it's a sodium chloride lattice or similar to that. Each positive ion, negative ion are the center symmetry. So there is no dipole moment, right? It's an inverse symmetry. There's no dipole. Now, what happens when you bring a little empty, show the oxygen atom, a little empty shell of D, so it likes to move and hybridize a lower energy. It's like, making friends, and when you make friends, if you are a good friend, they can lower the energy. So it does. But it costs you elastic energy to destroy. But once it mixes it, hybridizes it, and breaks the inversion symmetry, P and D, if you think about one is odd, one is even, so inversion symmetry is broken, and proportional to hybridization, and then the net dipole moments, if they interact, then that energy also helps you in energy. So you break the inversion symmetry by atomic displacement, but the gain you get is through hybridization energy and dipole energy. So similarly, that was well understood, and the beautiful work by Hill on the ferroelectricity origin of D0ness. Then the question is whether that will have an empty d orbital. Can it give rise to some ferromagnetism or interest in magnetism? Is what we thought about.
The other symmetry will break down, or that will also satisfy?
Yeah, but if you think about it, in a magnetic system, time reversal symmetry is broken, right? It becomes magnetically ordered. Now, inversion symmetry doesn't change in this case, but of course, magnetism leads to new ground state. If you think about it, unfortunately, in this system, the the entire ordering is still antiferromagnetic. Even if the layers are ferro, so the layers symmetry is broken, right? Ferromagnetism breaks time versus symmetry. If you only look at the layers symmetry of time symmetry, they are broken because they're ferro. But the global symmetry is ferro, antiferro, that still is antiferro, doesn't break. But if I can make one layer, monolayer, then I can break the time reversal symmetry by tuning this hybridization. Say, for example, you have one monolayer of tellurium atom size system, one monolayer of tungsten. So if I change tellurium to tellurium, then I break the time reversal symmetry. So in a way, something similar is happening here also.
Okay, sir. Thank you, sir.
Thank you. What's your name?
Sir, Rosman.
Well, thank you. Nice.
Okay, sir. Thank you for your nice, wonderful talk.
Are you Profilo?
Yes, sir.
I can't recognize you with your mask and so on. A little bit. Because I could see Profilo, I want to see without mask. Oh, okay. Nice to see you. Yeah. Okay. I'm sorry, I just couldn't make it. So maybe it would have been nicer. Okay. Thanks. Anyway, thank you for asking me. And Durga said, sir, can you just to my pleasure. More we have come here till March. I usually come after we are here till March.
Yeah, if possible, we can have the
regular seminar. Yeah. I would love to do. Maybe let's wait till January. Right? It will be better in January.
February, March.
February, March. Good. Yeah. So at least I'm sure that I don't have any COVID. You don't have COVID, and because we're worried if you come through aeroplane and so on, people from all over are also in the plane. Although they're very careful planes, but you never know. And even if we're all vaccinated and also had taken booster, but old age.
You take the booster.
Exactly, we took booster. Otherwise, I wouldn't have come. We're old people. So we have to be very careful. But on the other hand, this new strand is breaking through the boosters also. So anyway, let's hope. I would love to come in February or March, and we're tentatively living on March 18th. But I would love to come. Yeah, let me know. And okay. Thank you, Profilo. Yeah, nice. Thank you, Nitesh.
Thank you. Good night, sir.
କାଲି 10:30 ଆରମ୍ଭ କରିବାରେ ପାଇଁ ଏତେ ଡେରି ପର୍ଯ୍ୟନ୍ତ ଟାଣିବା